So our next talk is on optimal release policy for covariate software reliability models.
Hi, good afternoon, everyone. Thank you for the opportunity to present my work. My name is Ebenezer Yawlui. My presentation is about optimal release policy for covariate software reliability growth model. So one may ask, what is optimal policy? So an optimal policy is a policy that maximizes the expected discounted return. So let's look at what we have. So past optimal release policies identify additional amounts of testing before software release, and they also consider software reliability growth models, but they do not identify specific test activities underlying defect discovery, and they often fail to consider uncertainties or iterative applications during software testing. And the vast majority of past software defect discovery models are just a function of time, and they only provide guidance on additional amount of testing required. However, our optimal release policy for covariate software reliability growth models explicitly link test activities to defect discovery, and we also determine the optimal allocation of multiple test activities that minimizes the overall cost of producing the software. So this research is based on the assumption that defects discovered during testing are less expensive. Fixing those defects are less expensive than defects discovered after testing, that is, after the software is released. So the goal of this research is to maximize defect discovery, minimize costs, and allocate resources in a manner that we can save some of the resources and our cost of producing the software will be less. So we have the covariate software defect discovery model, which is based on a discrete cost proportional hazard model with NHPP and software reliability growth model. We have the mean value function, and we have the mean value function represented as M of X, which is the probability or which helps us predict the number of defects detected in the up to and including the nth interval. And we have omega, which is the number of defects that will be detected in the infinite testing. And we have PS of I. And this PS of I function is the probability that a defect is detected in the ith interval, given that it has not been detected in the previous I-1 interval. And we have X of I, which is a covariance associated with Yi, which is the number of defects that is discovered in the ith interval at the time of testing. And we have gamma, which is a vector of the model parameters contained in the hazard functions. And we have beta, which is a vector of the model parameters. And we have G, which is a discrete cost proportional hazard model. And we have H, which is a baseline hazard function. So in this research, we can incorporate a lot of hazard functions into it, but we decided to use 3 of them, which can be incorporated in the PS of I function. So these 3 hazard functions are geometric hazard function, and we have the negative binomial of order 2, we have the discrete YO. And also, we formulated a low likelihood function, which is used to estimate the parameters of the discrete proportional hazard model. And we also estimated the maximum likelihood of the model with R covariates and gamma parameters to obtain the other parameters by solving a system of equations. So we have our optimal test allocation based on cost criterion, which is a model M small hat of X fitted to test activities and vectors of observed failures Y. We seek to allocate resources to test activities in interval n+1 in a manner that minimizes cost. So statistically, we represent it as minimum C of X, and C of X is the total cost to release the software. And we have X, which is the activities or the resources allocated to R covariates in the n+1 interval, subject to a unit cost of alpha I, and it is bias constrained with B, which is greater than 0. So the specific form of the cost formulation is represented as this. And we have alpha pre, which is the cost of removing defects before release. And we have M small hat of big X, which is the estimated number of defects that will be detected in the software during testing. And we have alpha post, which is the cost of removing defects after release of the software. And we have M small hat of X, which is the estimated number of defects that will be discovered throughout the software lifecycle. And the final term is the cost of all test activities up to the n+1 interval prior to the release of the software. And for illustration purposes, we employ the DS1 data set by Shibata and al. 2006, which has n equals 17 weeks of observation with 3 covariates. which is execution time in hours, failure identification time in person hours, and we have the computer failure time in hours as well. We have a corresponding failure. So specifically for illustration, we use the covariate E and C for plotting our graphs and doing illustrations. So the first graph says that for us to be able to achieve a minimum or a cost minimum, we need to allocate zero resources to test activity E, but we need to allocate 22.51 to test activity C to achieve a minimum of 561. And it also says that values greater than what the model recommends to be allocated to each test activity increases the cost. So with the graph, you could see that we achieved that minimum. And we also did a budget constraint, which we have 40 resources to be allocated. And the model still predicted that only 22.51 of those resources are needed to achieve that cost minimum. So values greater than V equal 23 does not reduce the cost further. And we did a superimposed version of the two graphs. We say that allocating additional amounts of time to test activity E, which is execution time, will not compensate for the cost of performing the test. So you can see from the contour plot here. So in summary, this research presented a software optimal release policy based on cost criteria, incorporating covariate software defect detection models. And we also allocate multiple alternative test activities based on budget constraints in order to maximize defect discovery. So our results suggest that optimal release policies based on covariate model provide direct guidance to software engineers on how to allocate effort across multiple test activities in a manner that minimizes costs and also maximizes defect discovery. So in the future, we would like to add more covariates where the dimensionality of the problem increases. And we also like to develop stable and efficient algorithms. And we also like to use online procedures to iteratively allocate test activities. So we'd like to acknowledge the National Science Foundation for supporting us in this research. Thank you.